Hello everyone, I am Rakshita studying Electronics and Communication Engineering in Sri Venkateshwara College of Engineering, Bangalore. Today we are gonna discuss on a subject Electromagnetic Theory, subject code BEC 401 of topic Gauss law and its application. Let's know about its introduction. Introduction to Gauss law. Gauss law is a fundamental principle in electromagnetism that relates the electric flux through a closed surface to the total electric charge enclosed within that surface. This law provides a powerful tool for analyzing the electric fields of various charge distributions. Let's move forward to the next slide. Electric flux and Gauss law. Electric flux. The electric flux is a measure of the electric field passing through a given surface. Gauss law. Gauss law states that the total electric flux through any closed surface is proportional to the net electric charge enclosed within that surface. Applications. Gauss law can be used to simplify the calculations of electric fields for symmetric charge distributions. Gauss law electric flux. Electric flux is the amount of electric field going across a surface. It is defined in terms of a direction or a normal unit vector perpendicular to the surface. For a constant electric field and the flat surface, it is easy to calculate. Denoted by phi e, units of Newton meter square per coulomb, phi e equal to ae into n vector, phi e equal to ae cos theta. When the surface is flat and the fields are constant, you can just use multiplication to get the flux. When the surface is curved or the fields are not constant, you have to perform an integration. Phi e equal to integration of e into n cap dA, where phi e equal to 0. Gauss law for continuous charge distributions. Continuous charge distributions. Gauss law can be applied to continuous charge distributions where the charge is spread out over a volume or a surface. Mathematical formulation. The mathematical formulation of Gauss law for continuous charge distributions involves integrating the electric field over a closed surface. Symmetry simplifications. The use of symmetry can greatly simplify the application of Gauss law to continuous charge distributions. Procedure. Divide the charge distribution into small elements, each containing a small charge delta Q. Calculate the electric field due to one of these elements at point P. Evaluate the total field by summing the contributions of all the charge elements. You can see the diagram on the screen. Let's move forward to the next slide. Gauss law for discrete charge distributions. Discrete charge distributions. Gauss law can also be applied to discrete charge distributions where the charge is concentrated at a specific point or locations. Mathematical formulation. The mathematical formulation of a Gauss law for discrete charge distributions involves summing the contributions from each individual charge. Symmetry considerations. Symmetry can be used to simplify the application of Gauss law to discrete charge distribution just as it can for continuous charge distributions. Applications of Gauss law in infinite plane. Infinite plane of charge. Gauss law can be used to easily calculate the electric field due to an infinite plane of charge. Uniform electric field. The electric field produced by an infinite plane of charge is uniform and perpendicular to the plane. Charge density dependence. The magnitude of the electric field is proportional to the charge density on the infinite plane. Real world application. This application of Gauss law is useful in understanding the behavior of the charged surfaces, such as in capacitors. Electric field due to an infinite plane sheet of charge, where sigma is equal to sheet charge density in coulombs per square meter, where sigma A equal to charge inside Gaussian surface, phi equal to E to A, that is equal to sigma A by epsilon naught. E equal to sigma by 2 epsilon naught. For an infinite sheet of charge, the electric field will be perpendicular to the surface. Therefore, only the ends of an cylindrical Gaussian surface will contribute to the electric flux. In this case, a cylindrical Gaussian surface perpendicular to the charge sheet is used. The resulting field is half that of a conductor at equilibrium with this surface charge density. By symmetry, the magnitude of the electric field E at all the points of the infinite plane sheet of a charge on either side end caps in and along the outward drawn normal for positively charged sheet. Applications of Gauss law. Infinite cylinder. Infinite cylinder of charge. Gauss law can be used to analyze the electric field due to an infinite cylinder of charge. Radial electric field. The electric field produced by an infinite cylinder of charge is radial, directed outward from the cylindrical axis. Charge density dependence. The magnitude of the electric field is inversely proportional to the distance from the cylinder axis and proportional to the charge density. Application of Gauss law in spherical charge distribution. Spherical symmetry. Gauss law is particularly useful for analyzing the electric field of a spherically symmetric charge distribution. Radial electric field. The electric field produced by a spherical charge distribution is radial, directed outward from the center of the sphere. Charge density dependence. The magnitude of the electric field is inversely proportional to the square of the distance from the center and proportional to the charge density. Limitations of Gauss law. Charge distribution symmetry. Gauss law is most useful when the charge distribution has a high degree of symmetry, such as planar, cylindrical, or spherical geometries. Complex geometries. For charge distribution with more complex geometries, the application of Gauss law becomes more challenging and may not provide significant simplifications. Boundary conditions. Gauss law does not directly provide information about the behavior of the electric field at boundaries or interfaces between different materials. Let's know about the advantages of the Gauss law. Simplification. Gauss law can be greatly simplify the calculation of electric field for the charge distribution with high degree of symmetry. Conceptual understanding. Gauss law provides a deep conceptual understanding of the relationship between the electric flux and enclosed charge. Broad applicability. Gauss law is a fundamental principle that can be applied to a wide range of problems in electromagnetism. Conclusion and summary. Gauss law is a powerful tool for analyzing the electric fields of various charge distributions, particularly those with high degree of symmetry. Applications. Gauss law can be applied to continuous and discrete charge distributions as well as specific geometries like infinite plane cylinders and spheres. Advantages and limitations. While Gauss law offers simplifications and conceptual insights, it has limitations for charge distribution with complex geometry or boundary conditions. Thank you for watching my video. Please do like, share and subscribe my channel.